This video is sponsored by Brilliant. Stay tuned to the end for a very special offer for Arvin Ash viewers. You and the world around you are made up of millions and millions of atoms. Heck, they're estimated to be more than 10 quadrillion vigintillion atoms in the observable universe. That's a 1 followed by 78 zeros. But what are atoms? Atoms are tiny particles made from electrons, protons, and neutrons, which are in turn composed of quarks. But that begs the question, where did these particles that make up the atoms come from in the first place? The short answer is the Big Bang. In the early universe, there was an immense amount of energy. Yada, 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 the energy condensed, atoms formed. But as you might suspect, there's a lot that happened in the yada, yada, yada step. So what really happened? What is the Big Bang really in a scientific sense? The answer, which might surprise you, is coming up right now. To understand what the Big Bang really is in a scientific way, we must take a closer look at what happened in the early universe. But to do that, we need to have some kind of a timeline. This means we need some place where the timeline starts. The truth of the matter is that while the Big Bang is often thought of as the theory explaining the beginning, it's actually not. We don't know anything concrete about when the universe actually started or whether it even did. The most we can do is use our best model of the universe called the Standard Model of Cosmology and use this to turn the clock back to get as close to the beginning of time as we can. But if we can do that, why can't we just turn the clock back to the very beginning at t equals 0? In short, the problem is our theories are incomplete, and at some point very close to the beginning of time, the theory becomes unreliable. The theory predicts a singularity, a moment in time when all the matter and energy in the universe, in other words, all of creation, was in an infinitesimally small point of infinite density. Most physicists believe that this is probably wrong. The best we can do is go back up to 1 Planck time, about 10 to the negative 43 seconds. This is the smallest unit of time that can theoretically exist according to quantum mechanics. We have no idea what comes before this. So although this is as close to the beginning as we can get, it's not quite t equals 0. Even to understand what happens here at t to the negative 43 seconds, we would need a quantum theory of gravity, because it is here where gravity, the theory of the very large, meets quantum mechanics, the theory of the very small, because all matter and energy, and thus gravity, would be confined, presumably, to the tiny scales of quantum mechanics. This 10 to the negative 43 seconds is considered the first epoch of the universe and is often called the Planck epoch, or era. Around this Planck epoch, we expect that there was a point at which all the forces, electromagnetism, the weak and the strong force, united with gravity, forming one grand unified force. So to build a timeline for our Big Bang theory, we start before the Planck epoch and set the clock to 0 at this point. Keep in mind that this is not really t equals 0, but we start here anyway because it's the best we can do without running into the singularity. There might have been something before, but we don't know. And we also don't know how the universe looked during this epoch or what happened. The earliest time that we can theorize what happened is around the time of inflation. This happened from about 10 to the negative 36 seconds to about 10 to the negative 33 seconds after the Big Bang. This is when whatever existed prior to this time, let's call it the singularity for convenience, grew exponentially fast, faster than the speed of light. This is permissible because there is no theoretical restriction on how fast space can expand. It grew from a point to about the size of a large orange. Now you might say, but I thought you can't break the speed of light. But actually you can. What Einstein found is that information can't be transferred faster than the speed of light. This ensures that you always have a cause and effect. Causality is preserved. But because cosmic inflation occurred faster than the speed of light, it means that 2 points in space that could affect each other before inflation, in other words, 2 points that were causally connected, might not be causally connected after inflation, since they moved apart faster than light. The things we currently understand occur mostly after inflation. So the proper way to understand the Big Bang is not some point or object from which the universe started or came into existence, but as a period in the early universe where the universe was very hot, very dense, and expanding rapidly. So the Big Bang is not what happened at t equals 0. It's everything that happened after that. Inflation is thought to have occurred from 10 to the negative 36 to about 10 to the negative 33 seconds. Where did the energy come from to cause this rapid expansion? This problem has not been solved. Cosmic inflation is a process that destroys any information about what came before it. The theory of the standard model of cosmology is really only well understood starting at about 10 to the negative 12 seconds because the universe at this point had energies that can be approximately replicated in current particle accelerators. Prior to this time frame, we can only speculate. So anything that we talk about prior to this is largely speculation. We can turn the clock scientifically almost all the way back, but not quite. We don't know much about what happened during the period after inflation, from about 10 to the negative 33 seconds to 10 to the negative 12 seconds. In terms of the forces, gravity is thought to have separated from the unified force shortly after the Planck epoch at 10 to the negative 43 seconds, and later the strong force is thought to have separated at around the time of inflation, 10 to the negative 32 seconds. But from 10 to the negative 32 seconds to 10 to the negative 12 seconds, the electromagnetic and weak forces were still united as the electroweak force. And at this point, the laws of the standard model of particle physics tells us the universe probably consisted of quarks and gluons existing together in a quark-gluon plasma, along with some other fundamental particles. But importantly, at this point, all these fundamental particles were massless because the Higgs field was massless at this point. In other words, it had not gained a non-zero potential that allows fundamental particles to gain mass by interacting with it. Where these initial massless fundamental particles came from is still not known. It's possible they somehow condensed from the energies present at the Big Bang, or there might have been an initial scalar field, similar to the Higgs field, called the inflation field, which consisted of inflatants that decayed to the fundamental particles we see today. As time ticks slightly forward to about 10 to the negative 11 seconds, and the temperature of this hot universe falls a bit further to about 10 to the 15 or 1 quadrillion Kelvin, the lower temperature and energies leads to something called electroweak symmetry breaking at the beginning of the quark epoch. What happens at this stage is that the electromagnetic and weak forces become distinct and separate forces. This leads to the Higgs field gaining a non-zero potential, which looks like a Mexican hat called a sombrero. This means that the fundamental particles that now interact with the Higgs field gain mass. This is how the particles of the standard model obtain their rest mass. If you want to learn more about the electroweak symmetry breaking and how the Higgs potential causes the particles to become massive, check out my video about electroweak theory. At this point, we have all the building blocks for atoms. Again, the time is around 10 to the negative 11 seconds after the beginning, and the temperature of this universe is around 1 quadrillion Kelvin. The universe is, however, still too hot for the quarks to combine together to form hadrons, like protons and neutrons. This changes as the universe keeps expanding and further cooling takes place. As temperatures cool to around 1 trillion Kelvin at 10 to the negative 5 seconds, the quark plasma turns into a hadron gas consisting of protons and neutrons and some mesons. The mesons are a combination of quark-antiquark pairs that eventually decay into photons and electrons. As the universe keeps cooling down, the antiparticles now begin annihilating with particles, creating lighter particle and antiparticle pairs, eventually ending up as the lightest particles, neutrinos and photons. While we would expect that an equal amount of particle and antiparticles would be created, this didn't happen. For some reason, more particles were created than antiparticles, about 1 in 10 billion more. The reason for this matter-antimatter symmetry is one of the biggest unsolved puzzles in physics. If this annihilation were symmetric, meaning the same amount of particles and antiparticles were converted, then we would have had a universe consisting of nothing except photons and neutrinos. That is, no quarks or electrons, and thus no atoms. Luckily, there were ever so slightly more particles than antiparticles, so that some quarks and electrons survived the annihilation, and protons, neutrons, and electrons that would eventually turn into the first atoms were able to be formed. This annihilation of particles ends with the lepton epoch at around the 1 second mark. The temperatures at this stage cooled down to around 5 billion Kelvin, Leptons are the lightest matter particles and therefore the last particles to finish this annihilation process. After this fire show, most of the matter particles in the universe had been destroyed and turned into photons and neutrinos. But as I said, because of the mysterious matter-antimatter asymmetry, a few protons, neutrons, and electrons were left over, the building blocks needed for atoms. Protons on their own are technically hydrogen nuclei. You can think of them as positively charged or ionized hydrogen atoms. But we're interested in where the stable neutral atoms come from. To do this, more time had to pass and physics had to do its thing. When the universe was a few minutes old, the temperature dropped below 1 billion Kelvin, and it reached the point of the Big Bang nucleosynthesis, also called the BBN. Initially, protons and neutrons were produced in equal numbers, but free neutrons are actually not stable, unlike protons. This is related to the fact that neutrons are slightly heavier than protons, making them less stable than protons. If left free, a neutron will undergo something called beta decay via the weak force into a proton in about 10 to 15 minutes. After the protons and neutrons were formed, the temperature was so hot that the conversion from protons to neutrons was equal to the conversion from neutrons to protons. But as the universe cooled down, this process changed, and the decay of neutrons began to dominate. As it turns out, neutrons can become stable when they're in a bound state with other neutrons and/or protons, but not on their own. So at this point in the story, it was a race against time for these free neutrons to bind to other hadrons to form larger nuclei before they decayed. The Big Bang nucleosynthesis lasts for around 17 minutes until the universe is around 20 minutes old. During this process, a lot of neutrons managed to form bound states and thus survive, but many decayed into protons, and this is why we have a lot more protons around today compared to neutrons. The result of this process is that the universe at about 20 minutes has a nucleon content of around 75% hydrogen and 25% helium-4, with very small amounts of deuterium, which is an isotope of hydrogen with an additional neutron, a very small amount of helium-3, and small traces of lithium-9 nuclei. The universe consisted of about 87% protons and 13% neutrons. So we see that most of the universe at this point is just protons, or hydrogen nucleons. Pay attention to the fact that at this point in time, it's all ionized nuclei, so only the core of the atoms exist, no electrons bound to them. In order to form neutral atoms, the negatively charged electrons must attach themselves to the positively charged nucleons to balance out the charges. The problem is that the universe is still so hot that the electrons can only attach to the nucleons for a split second before being ripped away, because they have so much energy. This also means that at this point the universe is still opaque. If you were there, you wouldn't see anything because the photons that carry light would be constantly interacting with nucleons and electrons flying around. They would not be free to propagate through space. The situation with the electrons and the nucleons is analogous to a spacecraft trying to orbit a planet. If the craft flies too fast, then it will fly out of orbit. So it needs to be slow enough for gravity to capture the spacecraft into an orbit around the planet. The same thing with the electrons. It can't get bound to the nucleon. Now, this photon epoch lasts for a very long time, about 380,000 years, until the universe cools down to 3,000 Kelvin. At this point, the electrons have so little energy left that the electromagnetic force can finally bind them to the nucleons for good and form stable neutral atoms. This is called recombination. This also means that the photons are no longer bound in this chaos of positive nucleons and negative electrons. They are now free to fly unobstructed through the universe, and we would be able to see this light if we were there in space. The consequence of this today is that everywhere you look, you can see this first light of the universe. This is called the cosmic microwave background, or CMB. This light was released as the first stable neutral atoms were formed. So the baby pictures of the universe that you see here is also the record of the first neutral atoms forming in the universe. I made a video about the CMB if you want to learn more. Now, the story of how the first atoms in the universe formed is only the beginning of the fascinating journey of atoms. It is a story of only how the lightest elements formed, hydrogen, helium, and lithium, and some isotopes. But as you know, we need a lot more than that for life to exist. So the next question is, how did the rest of the elements of the periodic table form? Particularly, where did carbon, oxygen, and nitrogen, elements essential for life, come from? That fascinating story will be the subject of my next video. So stay tuned for that. In the meantime, if you want to learn about how atoms, which form the molecules that take part in the rich landscape of chemical reactions, you will love a course called The Chemical Reaction, available on Brilliant, today's sponsor. In this course, you'll learn the fundamentals of chemistry from the perspective of chemical reactions. It's a fun way to learn because you solve puzzles and patterns to see how charge, energy, and probability combine to determine the behavior of molecular reactions. It's different than the usual quantum mechanical approach, and you'll end up learning and retaining more information because of the interactive aspects of this course. Brilliant has a special offer for Arvin Ash viewers right now. If you're among the first 200 people to click the link in the description, you'll get 20% off your subscription. If you haven't tried Brilliant already, this is a great opportunity to start. So be sure to click the link in the description. And if you have a question, please post it in the comments and I'll do my best to answer it. I'll see you in the next video, my friend.